All right, good afternoon, evening, or morning, ladies and gentlemen. Welcome back to another episode of CS341 Algorithms, where today we're going to talk about NP completeness and the first NP complete problem, the satisfiability problem, or SAT problem. Okay, so the first thing we're going to get into is the complexity class NP complete. So we've seen the complexity classes P and NP. We're going to see NP complete now. So what is this complexity class? I'm gonna abbreviate it to NPC throughout this lecture and the next one. So this complexity class NPC, it denotes the set of all decision problems pi that satisfy the following two properties. So pi is in NP. Sorry, let me just add my laser pointer here. So pi is in NP. So this you have to be in NP to be NP complete. And then for every other problem pi prime in NP, there's a polynomial transformation from pi prime to pi. So that means that pi is NP complete. Okay. So this is sort of a weird definition. Here we have a problem that's in NP, and every other problem in NP can be transformed in polytime into an instance of this problem. Then this problem is NP complete. So this is like a transformation target. You can take every NP problem and transform it into this problem. That makes this an NP complete problem. This is kind of a strange problem in some sense, because this would describe a problem that's so expressive that you can express every other NP problem as sort of like a variant of this problem with only polynomial time overhead to transform from that other NP problem into this NP complete problem. So this represents really a super expressive problem. Now, note that this definition doesn't necessarily imply the existence of any NP complete problems. It doesn't immediately follow from the definition, because it may just be that there are problems in NP that can't be reduced to each other in polytime. It may be the case that there's some pair of problems, pi 1 and pi 2, where pi 1 cannot be reduced. I've said that backwards, or I've said that incorrectly. So it may be the case that there is no problem pi such that every problem in NP can be reduced in polytime to pi. There might just be sort of enough differences between problems in NP that there's no single universal problem that you can reduce every other NP problem to in polytime. And in fact, it might be a little bit surprising that NP complete problems exist. There are NP complete problems, and actually quite a few of them, that are so expressive and so universal that you can reduce or transform every other problem in NP to each of these problems. Each of these problems that are NP complete are expressive enough to represent every problem in NP with only polynomial time overhead necessary to transform problem instances. Okay. So here's an interesting theorem about the complexity class NPC. So if there's any problem that's NP complete, but that also has a polytime solution that's in P and also in NPC, then actually there's no difference between P and NP. The two complexity classes will collapse and become identical. So let's see why that's the case. Well, we said earlier, I think 2 or 3 lectures ago, that P is a subset of NP, right? If you can solve a problem in polytime, then you can solve it in polynomial time with access to a non-deterministic oracle. Because all you have to do is take the polytime algorithm for solving it and run it, and just ignore the non-deterministic oracle. And okay, sure, adding the non-deterministic oracle doesn't grant you any extra power because you don't even use it. But, I mean, you're not obligated to use it. You can just take your polytime solution, ignore the non-deterministic oracle, and solve the problem in polytime, and you have a non-deterministic polytime algorithm. So whether it's non-deterministic polytime just means whether you have access to that non-deterministic oracle or not. If it's solvable in polytime, it's also solvable in non-deterministic polytime by just disregarding the non-deterministic oracle. So it suffices here to show that NP is a subset of P. Then I could show that P is equal to NP. So I'm going to try to prove this theorem. We're going to suppose there is a problem that's in P and also in NPC. And we're going to show that that means NP is equal to P. We're going to do that by showing NP is a subset of P. Okay, so suppose pi is such a problem. It's solvable in polytime, and it's also NP complete. And we'll consider any other problem pi prime that's in NP. We're going to show that pi prime is also in P. And we're not assuming anything special about pi prime. It's just any problem in NP. So if we can show this, we will have shown that every problem in NP is solvable in polytime, which means P actually collapses, NP collapses into P. Okay, so since pi prime is in NP, and pi is NP complete, it follows that we can transform from an input to problem pi prime to an input to problem pi in polynomial time. That just follows from the definition of NP completeness. NP completeness says there's a polynomial time transformation from every problem in NP to this problem in NP complete. So there is this transformation from pi prime to pi. And now, if we have this transformation from pi prime to pi, and then pi is also solvable in polytime, well, we can construct a polytime reduction from pi prime to pi by taking an input to pi prime, transforming it in polytime into an input to pi, and then running our polytime solution to pi. That'll solve the problem, and it'll follow that we have a polytime solution to pi prime. And if you want to see that, the polytime part of that argument works out, because we have one, polytime function here, the transformation function, then we have another polytime algorithm, and we're sort of running a polytime transformation to produce a new input, then running that input in another polytime algorithm. You want to see all of that is polytime in the input to the larger problem, the problem we're trying to solve, pi prime. Okay, so and that's actually something that we argued in the last lecture, as we proved basically this line 2 here is proved as a lemma in the previous lecture. So take a look at that if you don't believe this or don't understand why this is true. So it follows that pi prime is actually solvable in polytime. And again, we didn't assume anything special about pi prime. So what we've argued here is that if we have this pi that's polytime solvable and NP complete, we've solved everything in NP in polytime. So P is exactly equal to NP. Okay, and this would be sort of a strange result. First of all, this question of whether P is equal to NP is not answered. This is the $1 million question, right? In fact, it might be a $2 million question at this point. And so if you want to prove that P is equal to NP, all you have to do is prove the existence of some individual problem pi that's solvable in polytime and is also NP complete. And this prize is not just for showing P is equal to NP, it's also for showing that P is not equal to NP. So if you can demonstrate the existence of some problem that is NP complete but can't be solved in polynomial time, that's also good enough to win you the $1 or $2 million. And we sort of strongly suspect that you can't show that P is equal to NP, that really P is not equal to NP, but it seems extremely hard to prove that. There are sort of practical reasons for thinking that P is probably not equal to NP. People have worked on this problem for decades, and it seems like no one's really even attempting at this point proofs that P is equal to NP. There are sort of philosophical reasons for thinking that maybe P should be different from NP. Because if they were equal, that would imply something very strange, philosophically speaking. It would kind of imply that the effort needed to explore a vast search space and discover a correct certificate is not that different from the effort needed to just verify a certificate that you're handed. And indeed, those problems seem quite different. Intuitively, this is like saying it's not really much harder to try to find a proof of some hard theorem than it is to just check that a proof is correct. And that would be a very surprising result, because the search space that you have to explore to find a correct yes certificate is often exponentially large in the size of the input. So the idea that these two complexity classes should collapse, and that would mean that, there is this clever way no one's thought of to search any huge exponential search space in polynomial time and get the right answer would be a very surprising result. Okay, so I'll stop waxing about that, and let's move on to talk about an NP-complete problem called conjunctive normal form satisfiability, or as we'll call it in this course, the SAT problem, or just satisfiability, or SAT. Okay, so what is this problem? Well, an input, or an instance, is a Boolean formula. So if you remember your logic course, you probably remember Boolean formulae that look something like this. So it's a formula that has n Boolean variables, x1 up to xn. Boolean variables are just true or false. And f, the formula, is going to be the conjunction, logical and, of a bunch of clauses. What are these clauses? These things in parentheses are clauses, and you can see these logical ands between those clauses. Each clause is a disjunction or logical or of literals, and a literal is just like a variable or the negation of that variable, so p or not p. Okay, so the variables here in this formula, this is a conjunctive normal form formula, a CNF formula, because we have a bunch of clauses separated by ands only. These are only ands between the clauses, and inside the clauses, these are only ors separating individual literals. Okay, and the variables are p, q, r, and s. The literals are p, q, r, s, not p, not q, not r, not s. The clauses are p or q, not p or r, not r or not p, or s or not s. Okay, and I'm writing the s as the not as like this logical negation. Okay. Okay, so that's the input. What is the actual problem we're trying to solve? Well, it's a decision problem, and the question that we're trying to answer is there a truth assignment to the variables x1 through xn? So in this case, to the variables p, q, r, s. Can I assign p, q, r, s true or false to come up with a single assignment of the variables such that this whole formula is true? And for this whole formula to be true, it means this clause has to be true, and these are ands in between the clauses. So this clause has to be true, and this clause has to be true, and this clause has to be true. So every clause has to be true, or satisfied, as we call it. So we say the whole formula is true or satisfied if each clause, all the clauses are true or satisfied. And each clause will be satisfied if, because these are all logical ors within a clause, if one of the literals, at least one of the literals, is true or satisfied. Okay? So, that means for each clause, a formula is satisfied if and only if for each clause, at least one literal is true under the particular truth assignment that we're trying to discover whether such a truth assignment exists to make the whole formula true or satisfied, okay? And this is, by the way, not just a strange theoretical problem. This is actually a real-world problem people really care about. So, for example, this problem is used extensively to argue correctness for new processor designs. So when you design new computer processor hardware in like Verilog or the VHDL languages, where you lay out all of these circuits and they want to prove safety properties about the circuits, it turns out you can express the safety properties in terms of these sorts of CNF Boolean formulae, and then you can run a program that solves the SAT problem called a SAT solver to figure out, is it possible for my safety properties I want to be true about my motherboard or my CPU to be violated? And okay, this turns out to be a really hard problem. This is actually the first NP-complete problem, which suggests it's an extremely hard problem. So it might be surprising to you that, in fact, SAT solvers exist and are well studied and are used in practice in industry to solve all sorts of problems by reductions to the SAT problem. So you can plug a real problem instance into a SAT solver and get an answer. And the trick is, even though SAT is theoretically a very hard problem, it's only extremely hard for some inputs, and some inputs can be run very fast. Turns out a lot of practical inputs can be run very fast, and there's a lot of power in having this sort of very universal, very expressive problem that you can reduce other problems to, and then a lot of very smart people can get together and write better and better and better solutions to this one very general sort of universal problem. So SAT solvers, there's this annual SAT solver competition where tons of money gets thrown at the best solutions for SAT solvers, and so it turns out, even though in theory this problem is so hard that it might take kind of until the sun burns out to solve a problem with like 100 variables and 100 clauses, in practice you can solve some SAT problems on some formula structures with millions of variables or millions of clauses in a small amount of time and get real very, very powerful results out of this technique. Okay, so it was a huge contribution of Cook and Levin in this Cook-Levin theorem to sort of put forth the first known NP-complete problem, which is the SAT problem. And this was the Cook-Levin theorem was part of the seminal work that really laid the foundation for this whole study of NP-completeness, which really gave a lot of computer scientists a brand new perspective on the hardness of problems. And it turns out NP-complete represents a huge class of problems that are all polynomially equivalent in terms of their expressiveness and their runtime complexity. And so this is a super challenging and powerful result. If you think about what it entails to prove a result like this from first principles, that SAT is NP-complete, how do you prove that any NP problem that anyone will ever come up with, no matter how smart they are, no matter how much time has passed, 1,000 years from now, if somebody else comes up with a new problem that's in NP, this Cook-Levin theorem proves that that new problem will be reducible in polytime to SAT. So that is a really, really hard thing to prove from first principles. I'm not going to do that here. I'm not going to show you how that proof goes. For this course, we'll just sort of believe that that result exists, that SAT is NP-complete, and we'll show, without working from first principles, how we're able to just take the existence of one NP-complete problem like SAT, and then via polytime transformations, extend what we know about NP-complete, the set of NP-complete problems, to grow the set of NP-complete problems that we're aware of. We can take this known NP-complete problem SAT, and via polynomial reductions, prove that new problems are also NP-complete. Okay, so let's see how you would do that. Now that we have one NP-complete problem, how do we show another problem is NP-complete? So given any NP-complete problem, say SAT, pi 1, other problems in NP can be proven to be NP-complete via polynomial transformations from pi 1. So from pi 1 to some other problem. We'll prove that other problem, pi 2, is also NP-complete. So let's see how that works. So suppose the following conditions are satisfied. So pi 1 is an NP-complete problem. Pi 1 can be transformed in polytime to pi 2. And pi 2 is also in NP. Well then, actually pi 2 is also NP-complete. Let's see why. So because pi 1 is in NP-complete, every problem in NP, every pi in NP, can be transformed in polytime to pi 1. Now if pi 1 can be transformed in polytime to pi 2, then every problem pi in NP can be polynomially transformed to pi 1, and then transformed from pi 1 to pi 2. So every problem in NP can be polynomially transformed to pi 2. Well, does that mean that pi 2 is in NP-complete? Well, not quite, because NP-complete requires that everything in NP can be polytime transformed to you, but also you have to be in NP. So we have to show that pi 2 is in NP. Well, that's fine. That's the third condition here. So if everything in NP can be poly-transformed to pi 2, and pi 2 is in NP, then pi 2 is NP-complete by definition. Okay, so that proves the theorem. So this is how we'll show that other problems are NP-complete. We'll take, for instance, SAT as a possible NP-complete pi 1. We'll reduce SAT to some other problem. That'll show the other problem is also NP-complete, because every problem in NP can be reduced to SAT and then to this other problem in polytime. So everything is also reducible to this other problem that's in NP. So this other problem is also NP-complete. Okay, so what I'm going to do in the remainder of this lecture is I'm going to show you how to prove that 3SAT, a specific specialization, a special case of the SAT problem, a different problem that represents a special case of the SAT problem, is also NP-complete. And there's a related special case called 2SAT that it turns out is not NP-complete and in fact is solvable in polynomial time. So I'll show you those two things. I'll show you the 2SAT result first, but first let me tell you what these are. So 3SAT is the same as SAT, except in SAT the clauses are allowed to have any number of literals. In 3SAT the clauses have to in SAT the clauses can have any number of literals, and the number of literals in two different clauses can be totally different. So you can have one clause with one literal and one clause with 100 literals and one clause with 7 literals. They can all be part of the same formula. In 3SAT, every single clause has exactly 3 literals. In 2SAT, every single clause has exactly 2 literals. Okay, these are the 3SAT and 2SAT problems. Let me show you here, just give you a sketch of a polytime algorithm to solve 2SAT. So first off, note here, here's an example 2SAT formula. This is satisfiable. Okay, so if P is 1, then this clause is satisfied. But this term is not necessarily satisfied by P being 1. So for this clause to be satisfied under the assumption that P is 1, I would need to set R to 1. Okay, fine, let's try that. So P is 1, R is 1. And then, here, if R is 1, this is not satisfied. And if P is 1, this is not satisfied. So this would not be satisfied by the selection P is 1, R is 1. So one of those has to be wrong. Okay, let's let P be 1, but let's let R be 0. Okay? So if P is 1, this clause is satisfied. This term is not. R is 0, this clause is not satisfied. I'm now realizing, looking at this, that actually my example here is incorrect. This is not satisfiable. So let me quickly correct this, and I'll restart. Okay, now I've fixed the actual example here. Let's set, so the first line is the same. The second line here, just what I said was the answer, was wrong. So P has to be 0, because if P is 0, if P is false, then this clause is satisfied, this clause is satisfied. And then if we set here P is false, so Q has to be true. And then it actually doesn't matter what we set R to. So there we go, this is satisfiable. Here's another example that turns out not to be satisfiable. But I'm going to show you how you can actually check algorithmically whether one of these formulae is satisfiable by reducing it, perhaps surprisingly, to a graph problem. We're going to end up reducing it to strongly connected components. So I'll show you how to do that. So our nodes for our graph, as we sort of transform a problem into a graph problem, we have to define what our nodes are and define what our edges are. Let me just make sure I'm recording so I don't, lose content. Okay, good. I'm recording. Okay, so we turn all of the variables in the formula into nodes. So we have variables PQR. We're going to have nodes PQR, and we're also going to turn the negations of variables into nodes. So we have not P, not Q, and not R. Okay? And then you have to, of course, describe what your edges are going to be. So what are our edges? Well, they're going to be the implications, the logical implications of each of the clauses. What do I mean logical implications? So if I do a little Boolean logic refresher here, remember that the implication P implies Q, or if P then Q, is equivalent logically to not P or Q. So if I look at one of these clauses here, let me get my laser pointer back. If I look at one of these clauses here, P or Q actually implies two different implications. It's equivalent to two different implications. So we could figure out what those are. I mean, logically, you can see not P or Q. You negate the P, and that's the antecedent, and you leave the Q the same, and that's the consequent. So if I negate the not P to get P, leave the Q the same, I get the antecedent and the consequent. So in P or Q, if I negate the P, I get not P implies Q. And I also get the, because these are symmetric around the or, I can put the Q before the P, I also get not Q implies P. You can also just think about this logically. If the P is false, then the Q has to be set in order for this clause to be satisfied. So not P implies Q. And if the Q is false, then the P has to be true. So not Q implies P if we want this thing to be satisfied. So for each of these clauses, we can define two implications. If the first term is false, the second must be true. If the second term is false, the first must be true. So let's write those down. So if the first term is false, not P, then the second term must be true, Q. So if not P, then Q. Not P implies Q. This is going to become an edge. We're going to make an edge from our not P node to the Q node. And there's another consequence we can get here. If not Q, then P. So we'll create an edge from not Q to P. And we'll do this for all of our clauses. I'll do it for one more. So if this literal is false, that means P is true. Okay, so if this literal is false, meaning P is true, this literal must be true, meaning R is true. So we have P implies R. And if this literal is false, so R is false, then this literal has to be true. So not P. So not R implies not P. Okay, and I'll leave these remaining ones for you guys as an exercise. You can pause and figure them out if you like. I'll give you a couple moments before I show them. Okay, so assuming you've paused, well, here are the remaining consequences. Here are the remaining implications of all these clauses. So now we have 2 times the number of clauses, implications, in the graph. 2 times the number of clauses as edges. Now, if we think about what these implications actually mean, it means, if Q is false, if not Q, then P. And if P, then not R. And if not R, then not P, and so on. So we can actually see, for example, as a consequence of Q being true, we must have P true. We must have not R, so R must be false. We must have P false. Well, wait a minute, that sounds like there's kind of a contradiction here, because we argue that P has to be true, and then P has to be false. And similarly, we can get from Q, by following a path in this graph, all the way to not Q. So if Q, then not Q. That's a problem. So Q implies not Q. Well, okay, maybe it's not a problem. What does it mean? If Q implies not Q, well, that just means if Q is true, we have a contradiction. But it's an implication. If Q is false, we learn nothing from the implication. So what this tells us is Q certainly can't be true, because if it's true, you get a contradiction. If Q true, then Q false. That's a contradiction. But this still admits the possibility that Q could be false. So, okay, what if we try the opposite? What if we try starting at not Q? Well, then we can go from not Q to P to not R to not P to Q. So we can get from not Q to Q. So not Q implies Q. If Q is false, then Q is true. Well, that's a contradiction if Q is false. So if Q is true, we have a contradiction, so Q can't be true. If Q is false, we have a contradiction, so Q can't be false. So that contradicts the assumption that the clauses are all satisfied, which is exactly where we get all of these implications of these edges from. So the assumption in this graph, if all these edges exist, is that all the clauses are satisfied. That's where all these implications come from. If this graph leads to this immediate contradiction that Q cannot be true and cannot be false, the assumption has to be wrong, that all the clauses are satisfied. So we can't satisfy all the clauses. Okay, so this was true because there was a path from Q to not Q and a path from not Q to Q for some variable Q in the graph. If there's any variable Q in the graph where that's true, there's a path from Q to not Q and a path from not Q to Q, then we're in trouble. Well, wait a minute. That's starting to sound, if I can reach you and you can also reach me, that's starting to sound a bit like strong connectedness. Okay, so it turns out that we can use strong connectedness to solve this. So 2sat can be solved in poly time. Suppose we're given an instance of 2sat on a set of Boolean variables. We'll name the Boolean variables just 1 up to the cardinality of x, like 1 to n. So just like we name the nodes in a graph 1 to n usually, we'll just name the Boolean variables 1 to n. So the clauses will contain like 3 or not 3, and 4 or not 4. And now, step 1 here is just how we build the graph. I showed you that on the previous slide. Step 2 is run Charrier's SCC algorithm or any SCC algorithm to get the strongly connected components of this graph. And then step 3 is, well, I is a yes instance if and only if there's no strongly connected component that contains x and not x. So here the not x is drawn as x bar, but it means the same thing, not x, for any variable x. So we can argue this to ourselves here intuitively. I'm not going to do a proof or anything. Let's just do this intuitively. So if there is a variable x that's in the same strongly connected component as not x, then we know there's a path from x to not x, and we know there's a path from not x to x. That means there's no way to assign x to satisfy the Boolean formula. So that gives us the only if. I is a yes instance only if there's no x in the same strongly connected component as not x. Okay, let's do the if direction. If there is, oh no, sorry, that's right. That's the only if direction. So if the only if direction is saying suppose there is oh, okay, it doesn't matter. I don't actually care about which direction is which. I don't want to confuse myself on the fly trying to over-explain this point. The point is we can easily argue to ourselves if there is an x and x naught in the same strongly connected component, then you get this x is true implies x is false implies x is true contradiction. On the other hand, if x and not x are in different strongly connected components for every variable x, if every x is in a different strongly connected component from its negation, then we know there might be a path from x to not x. But if there is, and they're in different strongly connected components, there's no path from not x back to x, and vice versa. So there can't be paths both ways if they're in different strongly connected components. And so suppose no variable is in the same strongly connected component as its negation. Then, how do we actually extract a satisfying assignment? Well, you can do the following. For each x, we want to figure out what the value of x should be, true or false. If there exists a path from x to x naught, to not x, then that means if x is true, then x has to be false. That's a contradiction. So we can't set x to true. So x has to be set to false. Otherwise, if there's no such path, that's fine. We can set x to true. And we can only do this if there exists a satisfying assignment, which is true if and only if there's no variable that's in a strongly connected component with its negation. So first, we build the graph, then we compute the SECs, then we check for each variable, am I in a different SEC from my negation? If not, if I'm in the same SEC as my negation for some variable, then I know there is no satisfying assignment. I say you can't satisfy it. If every variable is actually in a separate SEC from its negation, then there is a satisfying assignment. So you can either return true if you want to solve the decision version of the problem, or if you want to actually say what is a satisfying assignment, you can follow this procedure to produce such an assignment. Okay, so that's an argument that you can actually solve 2-sat in polytime. Now, how about 3-sat? You would think that the difference between 2-sat and 3-sat probably shouldn't be that big, but it turns out the difference between these two is about as big as we know how to describe. It's an extremely big difference. 3-sat is NP-complete, meaning you can solve every problem in NP by a polynomial time reduction to 3-sat. But 2-sat is solvable in polytime, which means you can't reduce any problem in NP that we know of to 2-sat in polytime, or else you'd have solved that million-dollar question that we were talking about. Okay, so let's prove that sat is actually reducible to 3-sat. You can transform in polytime an instance of sat into an instance of 3-sat. You have a polynomial transformation from sat to 3-sat. That'll prove that 3-sat is NP-complete. Okay, so let's suppose that x comma c is an instance of sat. What's x comma c? X is the number of, it's the names of all the variables, but let's just assume for simplicity that the names of all the variables are 1 up to n. And so this x term is actually kind of redundant as long as we know how many variables there are, which you can kind of figure out by looking at the set of clauses here. So imagine C is a list of clauses, and each of the clauses contains a bunch of literals, so a list of literals, and the literals contain the name of a variable in 1 to n, and some bit saying whether that literal represents, p or not p, a negation bit to say whether it's the negation of that variable. Okay? So we'll let x comma c be an instance of sat, but I mean, really, we could just think of c existing. If I were to implement this, I would really just have c. Okay. So C is going to be a sequence of clauses, a list of clauses. Here it's drawn as a set, but again, if we were actually to talk about the bit complexity, which we will soon, let's think about C being a list of clauses, and each clause is a list of literals, and each literal is the name in 1 to n of a variable, and a bit to specify whether it's a negation of that variable or not. So here's how we're going to take this sat instance and produce a 3-sat instance. Give me a moment to sip some water here. So for each clause in the sat instance, we're going to do the following. And okay, I'm going to jump right to case 2, which looks a little weird. But I think case 2 is a little bit easier to explain than case 1, so let's do case 2 and pop back. You'll see why I numbered them this way. So consider this clause in the sat instance. this clause in the sat instance can have any number of literals, right? And we're trying to transform this sat instance into a 3-sat instance where every clause has exactly 3 literals. So suppose this clause in the sat instance has 2 literals, z1 and z2. So the clause is z1 or z2. What we're going to do is we're going to construct 2 clauses containing 3 literals each. So we have z1 and z2 in each of these 2 clauses. So if either z1 or z2 is true, so if the original clause is satisfied, then both of these new clauses are satisfied. But we also want to make sure that if you satisfy both of these clauses, then the original clause is satisfied. That's sort of, I'm jumping ahead to how we're going to argue correctness, just to give you some intuition about the reduction. We want to make sure that in our 3-sat instance, these 2 clauses are satisfied together if and only if this clause in the original sat instance is satisfied. So here's what we're doing. We're adding a new sort of dummy variable c that isn't used anywhere else in the formula. It's a new variable that doesn't appear anywhere else in the formula. And we're sort of adding it to pad out this clause from 2 terms to 3, right? But we're letting this variable occur as a positive literal in one of the 2 clauses and a negative literal in the other of the 2 clauses. But why are we doing this? Well, the idea is to satisfy both of these clauses in the 3-sat instance. We can't satisfy both of these clauses with any particular setting of c, right? Suppose we let z1 and z2 be 0. Can we satisfy both of these clauses? No, because we would have to set c to true to satisfy this one, and we have to set c to false to satisfy this one. So in order for both of these to be true, we need one of the z terms to be true. So that's kind of the key insight here, is we're adding a dummy variable, but we're making sure that the addition of this dummy variable doesn't change the answer. In order to satisfy both of these clauses, we have to satisfy the original clause. And if the original clause is satisfied, both of these clauses are satisfied. So in some sense, we're constructing an equivalent pair of clauses that together are equivalent in the 3-sat instance to the single clause with 2 literals in the sat instance. So this is the key property. These 2 clauses are satisfiable if and only if the original clause of 2 literals is satisfiable. Okay, now I'll pop back to case 1. What if our clause in the sat instance contains just a single literal? Let me take another sip of water here. So in this case, we need to pad our clauses to have 3 literals each. So we're going to add 2 dummy variables. So it's a similar trick, but with 2 new variables, and we're making sure that the key property that we satisfied down here remains true here. Like here we said these 2 clauses can both be satisfied simultaneously if and only if this original clause is satisfied. Well, same thing here. These 4 clauses can only be satisfied simultaneously if z is true, if this original clause is true. So these 4 can be satisfied if and only if z is true, which is equivalent to saying this original clause in the sat formula is satisfied. Why? Because suppose z is false. Well, I have to set one of a or b true to satisfy this clause. And regardless of which I set true, this 4th clause will not be satisfied. So z has to be true in order for all 4 of these to be satisfied. So we're including all the combinations of a and b, plus a minus b, minus a plus b, minus a minus b, intuitively, so that no matter what our choices of a and b are, we can't satisfy all 4 of these clauses unless z is true. So we've constructed 4 new clauses that, taken together, are equivalent to the single clause in the original sat instance. Okay, case 3 is what if our clause in the sat input has 3 elements already, 3 literals already. Well, then just leave it unchanged and add it to our 3-sat input. No problem. Then that clause in the sat instance is satisfied if and only if the single clause in our 3-sat instance that we add in its place is satisfied. Okay, so that's easy. Now case 4 is where things get tricky. What if the clause in the sat instance is really big? It's bigger than 3 literals. We can't simply pad it out by adding extra variables, then we actually need to split it up into multiple 3-element clauses. So then we have to kind of link those clauses together so that the crucial property that all of the clauses together are satisfied if and only if the original clause in the sat instance is satisfied. We have to link them together with variables. So we create these new variables. So what we're going to do here is we're actually going to construct, if you have a clause in the sat instance that has at least 4 literals, and they're labeled z1 up to zk. So k would be 4 in that case. If the number of literals is 4, k is 4 here, right? So we have these literals z1 to zk. We're going to construct k minus 2 new clauses. So roughly as many clauses as there are literals, but minus 2. And we're going to create all of these clauses with 3 elements. We're going to link them together with these new dummy variables d1 up to dk minus 3. Why is it k minus 3? Because there are k minus 2 of these clauses, and we have 1 fewer of these variables than we have clauses. So each of these variables is going to link a clause conceptually to the next clause. Well, what do I mean link? Well, if you think about what's happening here with the introduction of d1 and negative d1, okay, so with the exception of the first clause and the last clause, every clause has a negative d variable linking it to the previous clause and a positive d variable linking it to the next clause. So we're sort of chaining these clauses together. And if you think about this, second clause here with z3 in it, if z3 is false, then somehow one of these two, negative d1 or positive d2, is going to have to be true in order for this clause to be true. So somehow that's going to help us. If we sort of think about how that's going to help us, the key idea is that we want to be able to satisfy all k minus 2 of these clauses if and only if some zi is true, because that's the case where we'll be satisfying this original clause. We want the original sat clause to be satisfied if and only if all of these clauses together can be satisfied. Okay, so let's sort of think about that intuitively, and we'll think about it much more carefully when we do the proof in a moment. But let's just think about it at a high level here to make sure we get the intuition before doing the proof. So if any of the z terms are satisfied, are true, then my claim is all of these clauses that we added should be satisfiable. Let's see why that's true. Well, if z1 is true, for example, then we don't need to set d1 to true in order to make this first clause satisfied. z1 will satisfy this first clause alone, so we can let d1 be false. That means negative d1 here will be satisfied in the second clause, and once this clause is satisfied by that initial term, we can let d2 be false, which satisfies the next clause, and so on. We can actually, from the point where we have our z1 true, all of the subsequent clauses can be satisfied, because we can just let all of the d variables after that point be false, which satisfies all of the subsequent clauses. Okay, well, what if it's some clause somewhere in the middle? What if z4 is true and none of the other z's are true? Well, then I don't need to set d2 any particular way or d3 any particular way to make this clause satisfied. So I can let d2 be true, which will satisfy this previous clause. Once this clause is satisfied, it can let the previous variable d1 be true to satisfy the previous clause. And again, if z4 is true, I don't need to set d3 any particular way, so I can let d3 be false, which will satisfy the next clause. And I can let that clause's d variable be false, which will satisfy the next clause, and so on. So if a z variable is set, then all of these clauses can be set to true by a particular choice of d variable assignments. And we'll explain that more in the proof. So that's if a z is true, then we can satisfy. What if no z is true? If no z is true, so this initial clause, input clause from the sat instance is unsatisfiable, we better not be able to satisfy all of these. So let's see why that's true. And again, this is an intuitive description. We'll see the formal description in a moment. So suppose all the z's are false. Can we make all these terms true? That would be a problem. Well, if all the z's are false, then I have to set d1 true to satisfy this clause. And then d1 false, here negative d1 will be false, and z3 is false, so I have to set d2 to true. Okay? So d1 is true, d2 is true, and because d true is true and z4 is false, I have to set d3 to true, and I have to set d4 to true and d5 to true, and so on, all the way up to dk minus 3 has to be set to true. But then if dk minus 3 is true, then this term, negative dk minus 3, is false, and zk minus 1 is false, and zk is false. So that means this final clause cannot be satisfied in that case if I satisfy this first clause. Okay, so that suggests if none of the z's are set, I can't satisfy all of these. And if any one of the z's is set, I can satisfy all of these. That should give you some intuition about why this set of k minus 2 clauses taken together are going to be equivalent to this single clause in the sat instance. So all these clauses in the 3-sat instance together will be equivalent to the single clause in the sat instance. Okay, let's try to prove that formally now. So let's prove that this is a correct polynomial transformation, and furthermore after that we'll prove that 3-sat is NP-complete. This will be most of proving it's NP-complete. There's one extra step to do that. Okay, so here's what we want to prove. We want to prove that sat, there's a polytime transformation from sat to 3-sat. Okay, so we described the transformation function on the previous slide. I described how we're taking clauses of the sat instance and producing one or more clauses of containing 3 literals to construct a 3-sat instance. So first we need to argue that that transformation function can be computed in polytime. Okay, so let's do that I'll sketch it here. I won't do a full proof. And it's a fairly easy sketch. So let L be the number of literals in the sat instance I. Remember, the largest number of clauses that we create is, well, let's think about how many clauses we create. In case 1, we create 4 clauses from 1. We start with 1 clause in the sat instance, we create 4 in the 3-sat instance. Case 2, we create 2 for 1. Case 3, it's a 1 for 1. Case 4, for 1 clause, we can, with k literals, we can construct k minus 2 new clauses. Okay, so let's relate how many clauses I create to how many literals there were in the original clause in the sat instance. So here there's 1 literal, and I create 4 clauses. There's 2 literals, and I create 2 clauses. There's 3 literals, and I create 1 clause. There's k literals, I create k minus 2 clauses. Okay, so the largest number of clauses that I create per literal is case 1, where I create 4 clauses per literal. So the number of clauses I create in my 3-sat instance will be at most 4 times the number of literals in the sat instance. Okay, so let L be the number of literals in the sat instance. In our transformed input, we construct at most 4L clauses. And clearly I can do that in time that's polynomial in 4L. So I just have to make sure I don't do, to construct 4L clauses, I don't do more than a polynomial in 4L work. And constructing, sort of clause lists that have literal lists that have, tuples, like pairs in those elements, that can all be done in a polynomial in 4L, like, 4L all squared or 4L all cubed. It's not hard to do that in polynomial time in 4L. Now, polynomial time in 4L is polynomial in L, which is polynomial in the size of I. Why? Well, the size of I has to contain, at least 1 bit for each of those literals, L, in the input. So poly size I is going to be poly something bigger than L or larger. Okay, so this proves that the amount of work we can do, this is at least a proof sketch, that the amount of work that we can do, that we're going to do is polynomial in the size of the input to the sat problem. Okay, so let's then prove this first direction out of these 2 directions we have to prove about the return values, about the correct outputs. Okay, so suppose I is a yes instance of sat. We're going to show that f of I is a yes instance of 3-sat. Okay, so if I is a yes instance of sat, there is a satisfying assignment, a satisfying truth assignment for all the variables that causes every clause to be satisfied, right? So every clause will have a true literal. So let x be any such assignment. Okay, we know there is a satisfying assignment. Let x be any satisfying assignment. We're going to consider each of the clauses in the instance I, and we're going to argue that the corresponding clauses in f of I are satisfied by the truth assignment that causes all of the clauses of the sat instance to be satisfied. Okay, so first, we're going to do this in cases. So suppose, we're going to go through all the clauses of the sat instance and say, well, this was satisfied, so consider the corresponding clauses in the transformed instance, all of those must be satisfied. Okay, so let's do that. So consider first the case where there's a single literal clause in the sat instance. Okay, then Z has to be true. If this clause is satisfied by the truth assignment for X that we fixed, Z must be true. Which means the corresponding 4 clauses that we created in f of I, well, those each contain Z, right? So all 4 of those have to be satisfied. Okay, next case. What if the clause in the sat instance has 2 literals? Then at least one of these has to be true. And the corresponding 2 clauses we create in f of I, both of those contain Z1 and Z2. So both of these clauses have to be satisfied. Well, the third case is the clause in the sat instance has 3 elements, 3 literals. Well, that clause occurs unchanged in our transformed input, so clearly that's satisfied as well. That leaves the only tricky case, which is suppose we have a very large clause with 4 or more literals in the sat instance. And suppose, ZT, one of those, Z1 to ZK, is true. Okay, one of those has to be true, right? Because this clause is satisfied by the truth assignment that we know exists, because this is a yes instance of sat. So if one of these Z has got to be true, let it be ZT. And the trick here is, think about all of those clauses, the k-2 clauses that we added in our 3-sat instance. So suppose I'll sort of show you here in this little diagram of all those clauses that I added what's happening, and then we'll run through the text here. So suppose ZT is Z3 here. Suppose T is 3. So suppose Z3 is true. Well then, we can, this clause is already satisfied, right? We don't need to set D1 any particular way or D2 any particular way to satisfy this clause. It's satisfied by Z3 being true. So we can let D1 be anything. In particular, if we let D1 be true, that will automatically satisfy this previous clause because D1 will be set to true. So we can let Di be true for all the i's that are less than t here. Well, less than or equal to t minus 2. So I'm sort of fudging the numbers a little bit here to explain it clearly, and I guess you can sort of see the off by 1 errors and whatever in my explanation. Well, you can see sort of how these exact numbers will work out if you read this carefully. But I think what you really need to understand here is the intuition behind what's going on. Whether you understand that this is a -1 or a -2 or just a t, that's not particularly interesting to me. I think it's very interesting that you understand exactly what's going on intuitively. But if you want to see why, look, if ZT is Z3, then T is 3, and T minus 2 is 1. So we let D1 and everything smaller be true, right? So you can see that. That's where the T minus 2 comes from. But I'd much rather you understand the intuition here. Z3 is true, so this clause is satisfied. So D1 and D2 are unconstrained. So we can let D1 and all the smaller, DIs be true to satisfy all the previous clauses. And then we can let D2 be false to satisfy the next clause. We can let all the bigger DIs be false to satisfy all the later clauses. Okay? So we'll define DI to be false for all the i's greater than or equal to t minus 1. Okay? That will set all of the other clauses to true, just because the fact that there was a true Z3 meant that we had this unconstrained D t minus 2 and unconstrained dt minus 1. So we have zt, dt minus 2, dt minus 1. Those d terms are unconstrained, which means we get to set them true to the left to satisfy all the left clauses and false to the right to satisfy all the right clauses. Okay? Okay, so that was one direction. Let's prove the other direction. So we're going to assume that the transformed input is a yes instance of 3-sat. We're going to show that the original input then that we transformed must have been a yes instance of sat. Okay, so let's see that. So here's how we're going to do this. We're going to consider each clause in the sat input, and we're going to argue that it has to be satisfied. So we have a yes instance of sat. Okay? So consider each clause in the sat input I. We're going to identify a corresponding set S of clauses in the transformed input that we, of course, created when we transformed this clause from I into a bunch of clauses in f of I. And we're going to show that because all those clauses in S are satisfied, because this is a yes instance of 3-sat, this clause C in the original sat input must also be satisfied. Okay, so let's see this. This is 4 cases. So first, suppose that the clause C in SAT that we're trying to show is satisfied has a single literal. Then we know we created in the transformed input 4 clauses of this form: ZAB, ZA not B, Z not AB, Z not A not B. And of course, these are all 4 of these together. We argued to ourselves earlier, all 4 of these can be satisfied together if and only if Z is true. In particular, because this is a yes instance of 3SAT, these 4 are all satisfied. And if they're all satisfied, that means Z is true. That means the corresponding clause containing just Z in I, in the SAT instance, must be satisfied. Okay, well, what if that clause C has 2 literals, Z1 and Z2? Well, then, in the transformed input, we created 2 clauses with 3 literals each, with this C and this not C. And we argued to ourselves earlier that if both of these clauses are satisfied, then one of Z1 or Z2 must be true. They might both be true, but at least one of them is true. Okay, so because this is a yes instance of 3SAT, these 2 clauses are satisfied. One of Z1 or Z2 must be true. That means this original clause, Z1, Z2, that we constructed these 2 clauses with 3 literals from, this original clause C, must be satisfied. Case 3. What if the clause C in the SAT formula has 3 literals? Well, then that clause occurs verbatim in the 3SAT instance, and it's a yes instance of 3SAT, so that clause is satisfied. That takes us to the final case, which is the only really complicated case in all of this. Suppose, case 4, that the clause C in the SAT instance is a large clause with at least 4 literals. So it has k literals, at least 4. And of course, we transformed it into k minus 2 clauses that have 3 literals each of this form, right? Okay, so if all of these clauses are satisfied because this is a yes instance of 3SAT, let's prove that the clause Z1 up to ZK must be satisfied. In order to prove this, let's just assume that that's not true, that all of Z1 to ZK are false. We're going to do this to obtain a contradiction, okay? So let's obtain that contradiction. Well, in order for the first clause, somehow all of these clauses are satisfied even though all the Z's are false. And we kind of walked through this intuitively, but let's just, do it formally here. All of the Z's are false, so this clause has to be satisfied because we've said this is a yes instance of 3SAT. So even though Z1 and Z2 are false, this clause has to be satisfied, so D1 must be true. But then for this clause to be satisfied, D2 must be true. And for this clause to be satisfied, D3 must be true. And this continues to here, where ultimately, in order to satisfy this clause, dk minus 4 was true, so dk minus 3 has to be true. So for this clause to be satisfied, everything all the way from D1 up to dk minus 3, for all these clauses up to this one to be true, to be satisfied, all of the variables from D1 up to dk minus 3 must be true. Okay, but if dk minus 3 is true, then this first literal is false in this final clause, and these 2 z literals are false, which means the last clause cannot be satisfied, which contradicts what we know about the execution, that this is, about the input, that this f of I is a yes instance of 3SAT. Okay, that's a contradiction, so our only assumption that all of the Z1 to ZK are false must be false. Okay, so one of those is true, at least one of them is true, which means the clause C in the original SAT instance I is satisfied. Okay? So what this means is we've given a correct polynomial transformation from SAT to 3SAT. So if a problem pi can be transformed into SAT in polytime, it can also be transformed into 3SAT in polytime. But wait, SAT is NP-complete. So every problem in NP can be transformed into SAT and then into 3SAT in polytime. So every problem in NP can be transformed into 3SAT in polytime. Does that mean 3SAT is NP-complete? Almost. To be NP-complete, you need to satisfy this property, and you also need to know 3SAT is in NP. Okay, so I could just tell you that 3SAT's in NP and you could believe me. And if you feel confident enough about showing that things are in NP, then you don't necessarily need to watch what I'm about to show you, although the way that I'm going to do this is slightly revised from last time, just to make it a little bit clearer. From last time I did this, I think I did it for Hamiltonian cycle, and before that for subset sum. This hopefully should be slightly clearer. So let's prove that 3SAT is in NP. So here's the sequence of steps. We first define the data type of certificates. This is a basic data type. So, int, string, bool, double, array of int, array of bits, array of char, array of double, right? I'm not talking about any fancy abstract data types like sets or maps, just something very simple, like what you would write as, intrinsic types in a language like Java or C. Notably, I'm not interested in data types like set or dict, which are first-order data types in Python, but are not in C or Java. We want to keep this really simple data types, okay, where you know exactly what the implementation is in memory. And if you want fancier data types, you don't define that for all certificates. You define desired yes certificate format, and then when you're verifying, you check if, if the certificate passed your verify function is a yes certificate or isn't by checking, does it have this very specific structure that matches my fancy yes certificate format? Okay, then we design a polytime verify algorithm, and you have to give a correctness proof. And so we'll run through these steps for, and of course, case 2 has a contrapositive, which we typically work with instead, because we'd like not to prove things about no instances or no certificates. We'd like to prove things about yes instances. Okay, so let's prove this for 3SAT. And first I want to define what a 3SAT input is, because in the process of telling you that I have a polytime verify alg, I'm going to need to be able to tell you what the size of the input is, which means I have to define what the input to the problem is really precisely. I have to pick some reasonable representation of the input. So let's do that. So the input will be a list of clauses. Each clause is a list of literals. Each literal is a tuple containing a variable name in 1 to n, so it's just a number, and a bit that specifies whether that literal represents the negation of that number or like the positive, the negation of that variable or like the positive variable. So it's a list of lists of pairs, okay? Okay, so what's our certificate type? It's going to be an array of bits. That's the data type. Now what's our yes certificate going to look like? Well, a yes certificate C is going to be an array with 1 bit per variable in our formula. Remember, the variable names are just 1 to n. So this is going to be an array with 1 bit per variable named 1 to n. So there should be n. It's an array with n bits, where n is the number of variables. And each bit is going to be true or false, representing what that variable should be assigned. And this certificate will represent a satisfying assignment that makes the formula true. That's a yes certificate. Now we need a polytime verify algorithm. So here's our verify algorithm. It takes as input our clauses. This is a list of clauses that are lists of literals that contain that are each a pair containing a variable, number, and a negation bit. Okay, and then we take the certificate C. So clauses is our input, and we have C. We can just figure out. We want to check. If C is a yes certificate, or maybe it could just be any sort of garbage information that we could imagine an oracle could give us. I've assumed the data type. I've assumed, just sort of as a shortcut, that the certificate's always an array of bits, something super simple. So we can assume that C is an array of bits. I want to keep that assumption very, very simple, just like an intrinsic data type in a simple programming language. Otherwise, if this is just a shortcut. Specifying a data type for the certificates is just a shortcut. If you didn't specify this, the first line of your verify function could be if C is not an array of bits, then return false. That's it. So this defining the data type is just a shortcut for not writing one extra check and verify. To me, defining the data type of certificates is not really a big deal. The important thing is your yes certificate defines sort of a fancy expression. It's an array with 1 bit per variable. There are n of those bits. It represents a satisfying assignment. But you don't know that the oracle is going to give you any of this stuff unless it's a yes instance that you're actually, unless clauses represents a yes instance, a problem input where the correct answer is yes. If it's a no instance, you might get all sorts of garbage, and that garbage in your certificate could look an awful lot like a yes certificate. So you can't trust the certificate much. You have to verify it very carefully against your input to guarantee that it actually is an accurate representation of the input if you're going to interpret it as a yes instance. Okay, so let's check, kind of assuming we know almost nothing about C except like the data type. It's an array of bits. Let's check to make sure that C, is a yes certificate, or prove to ourselves that it's not and return false. Okay, so here's how we're going to do it. We're going to first of all see how big is the certificate C, because if it's a no instance, it might give me, the Oracle might give me some gigantic certificate, and I better not iterate over the length of the entire certificate, for example, because if I did that and it gave me like an exponentially large certificate, I might take exponential time to do my verification. So let's just do a length check. So what do I know about the length? If it's a yes certificate, the length should be the number of variables, n. So let's just extract the number of variables from the clauses list. I'll just iterate over, so that's what's happening here at lines 2 and 3. I'm going to, imagine these lines are iterating over all the clauses, iterating over all the literals in the clause. Remember, clauses is the input. We aren't getting garbage data here. This isn't provided to us by the Oracle. This is the input. This is a well-formed input to the 3-sat problem. So I have to iterate over all the clauses, over all the literals, and just see what's the biggest variable number that I see. That'll tell me what my n is. Then I just check. If the length of the certificate is n, then keep going. But if it's not n, then I know this is not a yes certificate, because a yes certificate would give me a satisfying assignment. It would give me one truth value for each variable. So if it's not n, I'll just return false immediately. So now at this point in the code from 6 on, I know that I have an array with 1 bit per variable. That is, by definition, an assignment. But I don't know if it's a satisfying assignment, right? So I need to check that. So numsat is going to be the number of clauses that are set that I've proved are satisfied so far. I'm going to iterate over all the clauses and check if this clause is satisfied. How do I do that? I iterate over the literals and see if any of those literals are satisfied. And remember, a literal is a pair consisting of a variable number and a bit that says whether it's negated or not. So I'm going to check. I'm going to try to see, does the assignment, maybe not a satisfying assignment, but does the assignment of truth values to variables in C, does that assign to this variable a truth value that causes this literal to be satisfied? Does it make this literal true? If so, that's what's happening here with this rather fancy check at line 12. If the truth assignment to var satisfies this literal, then because the literal is satisfied and the clause is an OR of a bunch of literals, it's a disjunction of literals, the clause is satisfied. So I increment the number of satisfied clauses, and I stop checking literals for this clause and go to the next clause. So I break out of this inner loop, go to the next clause in the outer loop. And this special test here, this looks like some strange voodoo testing. My claim is that line 12 tells you whether the truth assignment to variable, to var, by the certificate C satisfies the literal, but the literal could be a variable or its negation. This is just a very compact way of expressing all the different cases where C of var is true and var is looking for not the negation, right? So if C of var is true, then and negative is false, then we've satisfied the literal. And if CFR is false but negation is true, then we've satisfied the literal, right? So that's just expressed here in this quick negation and equality check, right? So if C of var is assigned to true and we negate that to false, and that's equal to negative. So if negative is false and the negation of C of var is false, then that means we're not looking for a negative, we're looking for a positive, and C of r is true. So we should continue. Okay, so this is sort of if I had more space in the slide, I could break out the 4 cases and express it that way. But anyway, this is just a very compact way of checking sort of all the 4 cases to make sure that the truth value assigned to var by the certificate C actually satisfies a literal L. Okay, so at the end, after we checked all the clauses, we have a number of clauses that have been satisfied, and we know how many clauses there are in total. That's the cardinality of the list clauses. So we just check. If the number of clauses satisfied is equal to the total number of clauses, we're done, right? We've satisfied every clause. And otherwise, there's a clause that's not satisfied, so we should return false. Okay, so we want to argue this is polytime, and it's correct. So arguing it's polytime is not too hard, because if you figure out how much time this whole algorithm takes, iterating over all the clauses and all the literals takes order 3 times clauses time. 3 times the cardinality of clauses, because it takes you the number of clauses times how many literals there are. And this is 3-sat, so there are 3 literals per clause. So it's order 3 times cardinality of clauses time to compute n at line 2. constant time at line 4, constant time at line 6, in all the iterations of the inner loop over all of the iterations of the outer loop. Like, how many times is the innermost block of code executed over all the iterations of both outer loops? Well, the total will be 3 times the number of clauses, or less, because we might break out early. So this is, and then the amount of work we're doing inside the innermost loop is constant time, and this return statement's constant time. So this is all order 3 times the cardinality of clauses time, and the input size has at least 1 bit per clause, right? You agree with that? So the input size is going to be, at least cardinality of clauses, and order 3 times the cardinality of clauses is a polynomial in the cardinality of clauses. So this is going to take polynomial time in the input size. Okay, let's argue the correctness quickly. So case 1 here, let I be any yes instance. We have to prove that there is some certificate that the oracle could feed to our verify algorithm that will cause our verify algorithm to return true. So I is a yes instance. So it's a yes instance of 3sat, okay? Then there is a satisfying assignment of the variables. We'll call it AS. And if we pass the input to 3sat, the formula, that is satisfied by this satisfying assignment, and we pass that satisfying assignment as the certificate to our verify function in the desired format, we will see when we execute verify that each clause contains a literal that's satisfied by this assignment. So verify will see that at the end numsat equals the cardinality of clauses, and it'll return true. And now, rather than proving case 2, we'll prove the contrapositive. So suppose the verify algorithm returns true given some garbage, maybe some garbage here as C. We're not assuming anything really strong about C. But we are assuming that verify returns true for some input and some certificate. So let I be any input and C be any certificate. Doesn't have to be a yes certificate. Could be a no certificate. That's the basic assumption. Just any I, any C. The I has to be an instance of 3sat. Okay. Then we suppose that verify returns true. Okay, so what do we know? Well, if we return true, then we return true only if numsat equals the cardinality of clauses, if we've satisfied all the clauses. So numsat has to have been incremented in each iteration of the loop over the clauses. And we only increment it once per iteration of that loop, because as soon as we increment it, we break out of the literal loop and go to the next clause. So it's incremented at most once per iteration of the clause loop, and it has to be incremented exactly once per iteration of the clause loop if numsat reaches the cardinality of clauses at the end. And we only increment it if we've proved to ourselves that that clause contains a satisfied literal, a literal that's satisfied by the assignment described in C. And it has to be an assignment described in C, because if we return true, that means we didn't return early in our failure cases, where we check if this thing really is some assignment of the correct number of variables. So we prove to ourselves that each clause really is satisfied by by the assignment given in C. So that implies the 3sat formula is satisfied by the assignment C. So this is a yes instance. I must be a yes instance. Okay, so that proves that this problem is in NP. So 3sat is in NP, and we've already shown that sat is it can be transformed in polytime into 3sat. So this proves that 3sat is NP complete. Okay? So here's a recap slide you can take a look at. I'm not going to go into detail on it. Thank you guys for listening. I'm sorry this is running a little bit longer than I wanted it to. And next time we're going to wrap up with hopefully something very short. It'll be the final section on another complexity class that we'll just talk about really briefly called NP hardness. And then the final complexity class we'll talk about is called undecidability. It contains problems that are actually impossible to solve. Okay, but we'll leave that for next time. All right. Thank you guys for your attention, and I'll see you next time.